So in this tutorial, I just wanted to give you firstly an overview of the exam paper. I know it's a way off, but we've covered quite a lot of material that will go into that exam paper. So I thought it might be interesting to see the structure of that. So we'll look at last year's exam paper, and then from that we'll focus in on the 1D optimization part of those questions that I'm covering in the 4 lectures this week. So I'm conscious this is at the end of the lecture notes, so if you're having this tutorial right at the beginning of the week, I'm going to point you to the lecture notes as well, so you can be as well informed as possible. So this is the front page of the exam paper. This was our front page that we had for the COVID conditions, so it's open book. Normally it being invigilated. Not sure what's happening next year. But the section A and section B structure is exactly the same as it's always been for the last however years, certainly the number of years I've been doing this module. In section A, I'd aim to give a sort of cover sort of short questions on every section of the module possible. And then section B, I will focus in on certain areas of the module for more detailed questions and testing, and in this way give you a sort of a thorough fair and thorough testing of the material we've covered. So let's have a look at section A. So section A had 4 parts, A, B, C and D, and as you'll see they'll cover the different sections. So what I'm going to just do here in pen is just write over the section of the module that it's relevant for. So first section is a Newton-Raphson method, and then comparing it with bisection. So this is the root finding bit. So I'll issue the solutions to this paper at the end of this tutorial, so you have that for a revision, and hopefully we'll issue links to other exam papers as we get nearer to the exams. I'm very conscious that you're not doing a January exam for this, you're doing a May exam, so this is still a way away, but it's a useful point to talk about it in some way. So that's the root finding. I say I am constrained by the exam notes. So constrained by the exam notes, the lecture notes. So that I regard as from my view of these exams is I regard those as the syllabus, and so any problems, should we say, that arise, we have questions which are will be based on that exam material, on that lecture material. That's my view on things. So that's section A. Section B is on ODEs, ordinary differential equations, is basically doing a leapfrog and a Ford-Euler method comparing. Again, if you've revised lecture notes, revised the tutorials, this should not be a surprise to you at all. Then we get on to some the matrices material, which we just done last week, which is this is the power method in matrices, part 3, and as you say, this is quite bookworky. And then finally, we also have a matrices bit and ODEs bit in part D, which is the boundary value problem here. Now you notice I haven't managed to squeeze in optimization in part A. It sometimes happens like that, but you'll see that there'll be 2 places where optimization is tested in part B. But in general, we try and overview as much as possible in part A, so that you basically got a pass, over 40 just by doing the section A, and then section B is sort of trying to nuance things more detailed questions. That's in part A. I'm not going to go into the solutions today. I will issue the solutions for you to have a look at. I want to go into so the one thing I will focus on today is what the topic of this week's lectures are, whether you're, which is 1D optimization. So for those of you who are doing this tutorial on Monday, I'm just going to go through the lecture notes. Hopefully for those of you who are doing this tutorial either Thursday or Friday, will have come across consumed the lecture videos and taken some notes on it. But this is essentially the golden section search, which we cover in the last two of the 4 lecture videos this week. You notice I'm cutting down the number of lecture videos. It turns out I would, under normal circumstances, I would do all the lectures in 10 weeks. But I'm going to distribute the lecture videos over 11 weeks essentially, right up to week 12. So that means I can then now issue less videos now, and hopefully you're working hard also in parallel on your coursework. So that will give you sort of more time to work on that. So this is a golden section search, and that's what I'd like you to work on today in the tutorial. So work through number 2. So I'll come back to that in a minute. Let's just look at the rest of the paper. Then come back to question 2. So question 3 has a bit on ODE. So this is your Taylor expansion that was based on Runge-Kutta. This what I consider the slightly harder derivations in this part of the module, and then you want to show how it's all related to Runge-Kutta. So understanding where this derivation comes from. So some of these longer derivations are important to know. You may not have to review all of it, but certainly you need to understand how it works and the important subsection. So the key section to understand how Runge-Kutta work is doing these Taylor expansions, in F to second order. So, and then finally we got this partial differential equation problem, which we covered in the matrices problem, which was again slightly harder, sort of matrix problem. Again, I'll issue the solutions to these as well, and you'll be able to see how it all connects together. And finally, we have the final part of the course, which we're not going to cover this week, but in the final 2 weeks of weeks 11 and 12 is 2D optimization. And this is where we have a quadratic function in x and y, and we want to first establish whether a maximum and minimum exists, and then search for the minimum. And the 2 techniques that I'm going to cover are gradient descent, and we'll do the practical on this method as well next week on the 2D optimization. It will be gradient descent and conjugate gradient descent, which are a pair of methods. You notice we've often been covering, it's a good way to learn. If you just want to remember what the different methods are that we're covering, often they're covered in pairs. We cover Jacobi and Gauss-Seidel. We cover a trio of methods in the root finding, but they're all sort of related to each other in speed. And in the ODEs we'll cover a few methods, but they'll all be related in terms of their accuracy and stability. Here we've got another pair of methods, gradient descent and conjugate gradient. So the conjugate gradient method is faster than the gradient descent, and it is the method of choice whenever you find a method here. So this we'll cover. You'll have the solutions to this when you go home, and we'll have a practical where I want to go through gradient descent, if you like, in using some MATLAB code to parallel what we're going to do in the lecture videos, which is sort of doing it by hand. Okay, so that's to come, and depending on where in the week we are, question 2 is either completely new to you or slightly familiar because you've had a lecture video. So let me now point you to the lecture. This is what I want to do in the breakout groups, is go through this material. So it's basically starting on page 59 of the lecture notes. This is page 59 of lecture notes. So hopefully you really are using these lecture notes as a very parallel document when you either watch videos or go through tutorials or whatever. This is kind of the very highly honed document. I mean, there are mistakes and I will correct them, but there's a lot of things that are really nicely laid out in these lecture notes that are really is your source of knowledge, and then hopefully all the other materials, the lectures and the in particular and the tutorials will sort of reinforce that understanding. So let me just go to the diagram first of all and then come back to that. The idea with golden section search is you're like bisection, you're starting with a initial, so this is your width of a line, and you're searching for the minimum along the line. So this is step I call step I, and this is the next step I plus 1, these sections. Now some people present it the other way around, they put the subsequent section below. It doesn't matter at all. So it's related to bisection, and it's called the golden section search. Okay. And basically the ith interval is between AI and BI here, and we define 2 points in either side of the bisector, basically x left and x right, and then we decide whether the function, so these different points are the key ideas, and this is what you've got to do. We decide whether the function is smaller on the left hand side than on the right hand side, and in this case we've got the function is smaller on the left hand side, so we select a new interval. Now the thing about the golden section search is it shares points between the previous right hand point and left hand point in the new configuration. So the right hand point before corresponds to the left hand point in step I, and the new end of the interval is ascendant right. And this efficient use of functions evaluation is one of the reasons that golden section is works so well, and I go into in the video. Okay, and then you select the new point, select the new interval. So what you need to do, determine what x left is and x right. I'll give you the formula, will be up there in a minute, and then select the new one. And the case where it's the other way around, where x right is smaller than x left, the function, you select the right hand bracket. And you can also look at the lecture videos if you like in this tutorial, that's fine. So you need a formula for x right and x left. Well, x right and x left are related to this ratio r, and we calculate it later on. Let me just first of all give you the ratio r, which is key to this, which is 1 over the golden ratio. So this is the key thing that we've derived. You don't worry too much about it if we're on the Monday tutorials, but this is 1 over g, which is the golden ratio, but it's just a number, minus 1 plus root 5 on 2. It's a number, it's about 0.618, 3 significant figures, and that's central to this method. So you know what r is, and then you can use the formulas. So as I said, sometimes it's not a bad thing to encounter the lecture notes slightly ahead of the lectures. Obviously, if it's weeks and weeks ahead, you're doing really well if you understand the material. But this is a case where I've issued the lecture notes on Monday morning, and you've got the material, and if you're doing the Monday tutorial, you need to sort of read the lecture notes as well ahead. But it's no bad thing because you've encountered it, and then when you find it in the lecture, you say, aha, I've come across this method, and you're sort of a little bit more receptive to the key points. So it's not a bad thing at all. So yes, so don't forget, in this case, Ri is the same as R, which equals the 1 over the golden ratio, 1 over Pythagorean ratio, and you basically at each time you want to calculate, you know what A and B are, you determine xi right, and then you turn x left, and then you want to determine the function values at f of x left and f of x right. So that's really the base. So you do f, then you do f of x left and f of x right, and you determine which of these two function evaluations is smaller in terms of evaluating the next step. So that really what I want you to focus on then is if you like, the first bit of this question is bookwork. Sorry, here we go. We're on question 2. So the first bit is really just that is contained within the lecture notes and the setting up the problem. And really, the thing I want you to focus on is this sort of example, and that's the one I'll talk through in the solution video. So if you've got this function cos x minus sin x, and you want to start off with these this interval, so a and b, a is 1, b is 3, you know what r is, you can determine what x left and x right are for one step. So you start off with a naught equals 1, b naught equals 3, and then you want to determine what x left is for I is 0, x right, and then you want to determine whether the function is less on the left hand side or the right hand side. Select the new bracket and then determine the x left and x right for the next step. Okay, so as I say, I'll issue the solution, but this is a way of sort of coming across this problem. Okay, I'll leave you to get on that.